solutions that we discussed were in Cartesian coordinates. We considered domains which were rectangular, and we considered the two different types of solutions, polynomial and separation of variables, right? So what we want to do today is basically develop the area stress function solution in polar coordinates. So we kind of abandoned polar coordinate for a while. I was even waiting for some of you to ask me, why did we spend so much time in the beginning going through all the formulations in polar coordinate if we are not going to do anything with that? Well, that's where we are going to use polar coordinates for a week or two to go through a number of what I would call very interesting solutions. Not that the Cartesian coordinate solutions weren't interesting, but they weren't as surprising. We could kind of compare the solutions with the strengths of materials. We kind of knew some of the stuff if you just consider the domains to be a beam, etc. But the solutions that we can get in polar coordinates, some of them you probably have never seen how you got them. So let's just look to see why we are studying polar coordinates. Just imagine a domain which is rectangular, and then there are some holes in it. And just a very simple case, if it is being pulled on both sides like that. Is this a problem that you think has any kind of application? Like, can someone think about any kind of realistic problem which requires you to find a stress, a strain, and displacement field in a domain which looks like this? Have you been to Pittsburgh? You all have been to Pittsburgh. You haven't been, Mike? You should go. So have you, if you have been to Pittsburgh, have you seen this bridge, which is like a yellowish bridge, Andy Warhol Bridge it's called? If you walk there next time, pay attention to the truss, and you see big rivets, right? If you consider those elements and you take the rivets out, what do you see? You see an element which looks like that you have a structure, a beam in this case, and then you have these holes in them. Now, this domain looks rectangular. What is the connection with polar coordinate? Why can't we just use what I already showed you, all those formulations? Let's just solve for this one too. Those holes. So it turns out that although the domain is rectangular, what we really care about is what's happening around those holes, because it turns out that the stress there is kind of a special. Does someone remember why the stress is a special around the hole? Why do we care about that? There is a stress concentration. I'm sure that in some elementary courses you have seen that the stress is a little bit larger around the hole, something like that, and then it kind of goes back if you go far away from the hole. But you never saw where and how this kind of formulation was coming from. This was given to you, you accepted, you calculated some stress concentration factors, and you moved on. So when we want to analyze a problem like that, we think about Saint-Venant principle. So you think that, if you are far enough from the boundaries, you can just concentrate on a hole, because that's what is important for us. And then you see then immediately why you would want to study this problem in polar coordinate. It's a hole, it's circular, and it's much easier to actually deal with it in polar coordinate. So you want to see what is the state of stress here, and the polar coordinate, if you remember, we had a situation like that, and it all makes sense. Well, it would be a lot of waste of time if studying the holes would be the only application. There are many other applications with polar coordinate formulation is a lot more useful. Another very important example and related here is when you want to study the corners. So imagine in a structure, in a part that you are studying, you have, let's say this is a part of a structure, and then you have a corner. And that corner, again, leads to a stress concentration. That corner is where you want to focus, and you want to actually analyze the state of a stress, a strain, and displacement there. And again, if you zoom in to that corner, what you see is something like that, and you will see that it's easier to analyze that again in polar coordinate. And another super important application of polar coordinate formulation is the study of a structure which has a crack inside. Do we care about that? Why would we care about the crack inside the structure? I'm sorry? The stresses are, again, it's a stress concentration. So although the crack looks linear to you, you will see that it's much easier to use polar coordinate formulation for that. Now, the reason I'm trying to motivate the polar coordinate formulation, because today we are going to derive a lot of things, and from Thursday on we are going to solve examples. So I want you to be motivated and to look at it as a very interesting formulation that is going to be applicable to a lot of problems that we are going to solve. Kingsley. Very, very related. Maybe. The answer is always maybe, right? That's a good answer. If we have a quiz on Thursday or not. We'll see. It all depends on how fast we move. So with all that introduction, let's start looking at the formulation in polar coordinates. Okay? So what we need to do is to go back and start from a strain, displacement, and then the constitutive laws. But I'm not going to derive anything. I'm going to kind of just write down the necessary part and refer you to the book to look at the other equations, because the list is long. And then we are going to look at one important solution, which we are going to look over and over again in the next few classes for different problems, which are really, really interesting problems to look at. Any questions so far? Everyone motivated? No? Okay. So let's just get us started. So let's review the formulation of field equations in polar coordinates. So we need to look at a strain displacement. And if you want the long list beyond what we can write in the class today, this is at the end of chapter 7. Kind of I skipped it, moved to chapter 8, and now I'm just giving you the polar coordinate formulation. Go back to chapter 8 for the examples. It's kind of what's happening. So if you remember, we had ER and E theta. So you can write the displacement vector in polar coordinate. Now the relationship between a strain and displacement is a little bit more complicated. Than what we know in Cartesian coordinate. So ERR, E theta theta, and then we have ER theta. And this is for definition for a 2D problem. So I write the kind of useful relationships for plane strain and plane stress. So for plane strain, sigma RR is lambda ERR plus E theta theta plus 2 mu ERR. And these are, of course, the constitutive relationships. So maybe I should have written here to be clear, stress strain relations. And then sigma theta theta, lambda ERR. These should not look surprising to you, right? Are we done? Plane strain. What is missing? One component is missing. Stress or strain? It's plane strain. So stress. Sigma ZZ is missing. What's happening today? Half of the class is missing and the others are all very tired. This never happened before. End of the semester. No, Tom and Valerie are in a conference. Clay is sick, but I don't know where the rest are. So sigma ZZ is not 0. It's plane strain. And of course, you can imagine what is coming next. The plane stress again, I'm writing stress-strain relations. So ERR 1 over E sigma R minus nu sigma theta theta E theta theta 1 over E sigma theta theta minus nu sigma R E R theta 1 plus nu over E sigma R theta. Done here. What is missing? Prabha? There's also EZZ, right? It's right? Making sure you are awake. Yeah, we saw that you can write the strain in terms of the stresses and also in terms of the other two strain components, just like in Cartesian coordinate system, we can do it here too. And then, of course, there are equilibrium equations. These are the last ones I write down, just that you see the form a little bit. So sigma R, comma R plus 1 over R sigma R theta, comma theta plus sigma R minus sigma theta theta over R plus FR equal to 0 sigma R theta, comma R plus 1 over R sigma theta theta comma theta plus 2 over R sigma R theta plus F theta is equal to 0. So I would put 3 points here, 3 dots. So meaning that you can look at all other equations in the textbook. I just don't want to spend more time writing down equation. And in section 7.6, everything is provided. I've checked all the equations are correct, so you can look at them there. So what we need is to put all these equations to get the biharmonic equation in polar coordinate system. So the last so-called quiz, I hope that class exercise, right? We don't call it quiz in this class. We kind of, the last time I asked you to derive the biharmonic equation. Do you remember what you did? If you want to spell it out in English, what exactly did you do to get biharmonic equation? Exactly. You basically took the stress, how it is defined by Eric, and then you used the compatibility. You have also used the stress-strain relationship, and then putting all together, package it for zero for body force. You almost all of you got that right, so you could derive the biharmonic equation. Correct? So if you do the same thing, you can also get the biharmonic equation in this coordinate system. So let me write the biharmonic equation here and then show you how the relationship between a stress and the area stress function is. As you may guess, it's never as easy as it was in Cartesian coordinate system for some reason, but think about all those exciting applications. So motivate yourself that everything is going to be good, because really those applications are very interesting to look at. If it is the first time for you to see how you would derive the stress concentration factor, and that is joyful, right? I'm sorry? I don't hear you. No. These are the examples we are going to go through. The class exercise will be in Cartesian coordinates, so it's kind of would derive from the homework problems, and then we go through. No. You still need to know more to be able to get those solutions. Okay. Now, let's look at the biharmonic equation. So, let me just add a heading so things are not complicated. Okay. So the good news is it still looks this way. Laplacian squared equal to 0. But, of course, right, the way the Laplacian is defined in polar coordinate system is not as straightforward as in Cartesian coordinate system. So you have the second partial derivative with respect to r, then you have another term 1 over r, the partial derivative with respect to r, and then 1 over r squared, the second partial derivative with respect to theta. You should remember, if you download your memory here, you should remember doing a homework where we looked at the del operator in polar coordinate. Does anything come back? Download it? Yeah, that's good. And with this definition, we just like in Cartesian coordinate, we basically define the power of 4 as Laplacian. Okay. So now we have that. So in polar coordinates, we also need to know the relationship between a stress and area stress function, right? So the stress potential which is the area stress function phi, now it is a function of what? It used to be a function of x and y. Now it is a function of r and theta, right? The relationships are sigma r 1 over r, the partial derivative with respect to r plus 1 over r squared, second partial with respect to theta. So it's not as neat as, you know, in Cartesian. Here, this one is nice. Sigma theta theta is just the second partial derivative with respect to r, and sigma r theta has a negative, just like in Cartesian, but it looks like this. So partial derivative with respect to r, and then the way the biharmonic equation looks like, if you apply that operator on phi, is a little bit more complicated. So remember last time when I asked you to, in the class exercise, when you derived the biharmonic equation, how many terms did you have? No, before you collected them, how many terms do we have on the left-hand side? 4, and then 2 are the same because you can exchange the order, and then you only have 3. Now, in polar coordinate, the form is much more complicated. So get ready. It's not that bad, right? So we have 8 terms. So 1 over r cubed, partial derivative with respect to r, and then 1 over r squared, and 1r. So you see, kind of there is a beautiful order here. And then there are these 2 terms, which are just partial derivatives with respect to theta, minus 2r cubed, and these are the mixed ones, comma theta theta r, plus one more term, a little bit more complicated, right? But you still see that the maximum number of derivative is still, the order is 4, and this is how it looks like. Okay, now we want to solve this, because I try to convince you that this solution in this coordinate system is actually very practical, very important. Because some of those solutions, when you go very close to a crack or a very sharp corner, you cannot really get good solutions from just blind finite element analysis. So one solution that we are going to look at is the so-called Mitchell solution. So let's see how that solution is developed. And the solution is very simple. It uses, again, separation of variables. So now we want to solve this equation. So we now consider the Mitchell solution. Again, this is not a French name, so it is actually Mitchell. So we looked at the biharmonic equation in polar coordinates. It looked a little bit longer than in this is how it looks like in polar coordinates, and now we are just starting to develop the solution, so you may have started. Separation of variables. It means that we write the solution as a multiplication of one function, which is just a function of r, and the other one, which is a function of theta. So we consider a solution which has this form. If we substitute this solution in the biharmonic equation, of course, this e to the power of b theta kind of stays, and then you have a polynomial. So let me write it down. So in the book, the way this has been formulated, the steps are missing, and I don't think if you really wanted to see what is happening, you won't be able to see at all. So that's why I'm spending a little bit of time on this to make sure that you see how it is going from that formulation to what we will see in a minute. So these steps are kind of missing in the book. So so e b theta is outside, and then this in parentheses, that's the order of derivative. So derivative of order 4. You are familiar with this notation, right? Using this kind of. Okay. So I just write what you would get. So if you substitute this form of phi into the biharmonic equation, and you are welcome to check, you can use MATLAB, Maple, just plug this in, and you will see that you are going to get a form like that. So how do we solve an equation which looks like this? That's an ordinary differential equation, right? Is it so let me first say that for this to be equal to 0 for any combination of theta and r, do you agree that this part should be equal to 0? Now, can we readily solve this? What's the problem? The coefficients are not constant. Does everyone see that? Because there is r in it. So it's a little bit complicated. What should I do? Yes, that's good. So I told you that differential equation is quite intimidating. With all the solutions which appear from time to time, and you don't know where they are coming from. Yes. Look at the form a little bit. I have to keep you awake tonight, and we have a lot of derivations, so doing my best. Is there any kind of order, some sort of beauty in this equation? What do you see here? Exactly, so the derivatives and the powers of r in the denominator. So whenever you see something like that, that should signal change of variables. No, it's just the general. No, we haven't. That's a good question. No. It's a part of the whole solution. No. So let's use a change of variable to make sure that we can solve this. And the change of variable, if you remember from differential equation, which I don't necessarily expect you, looks like something like that. So if you change r, basically you change r to c, and this is the same way of writing you can write it either way. And then if you use the chain rule, and one thing about log, a lot of people, this is something that people have different opinions about. So when I write log here, I mean natural logarithm. That doesn't mean base 10. This is in different communities, it's being viewed differently, but we use it in this class as having the natural basis. So now, if we do this change of variable without walking you through the details, this equation here becomes simpler. And the meaning of derivatives are different. So in here, when we talk about derivative, on the top is derivative with respect to r. When you look at the bottom, this derivative is with respect to the new variable c, right? We changed the variable to be able to do that. Just pay attention to that. Okay. Now this equation, does this look easier to solve? Yeah, most importantly, the coefficients are constant, so we can easily solve it. Do you happen to remember what type of solution is good for this kind of partial differential equation? Exponential, exactly. So that's what the experience is. You see, now you know what kind of solution to expect. So we explore solutions which have this form. And now we view f to be a function of not r anymore, but c, and this is e to the power of xc. And then what do? You substitute this to the equation and you get a characteristic equation back, right? With all coefficients being constants. So without showing you how I get it, but that's easy to do, and something that if you had one afternoon and nothing better to do, you can just try, right? So the associated characteristic equation is a squared plus b squared s squared minus 4a plus 4 plus b squared equal to 0. So the roots are a plus minus ib. So I is here the complex, the imaginary unit, and then for the other part we have a 2 plus minus I b. Or you can write b in terms of a okay. So now we have something to look at. So let's look at the structure of this solution. So let's look back at the solution that we assumed. So we started with this kind of solution, right? So we have a function of r times e d theta, and walking you through this whole process, now we finally have something for b to look into. Now, what kind of solution do we consider? What does it make sense? Sorry, Paula. I'm sorry. Yeah, one thing is that we want the solutions to be real, and the other thing is that, remember, we want to develop solutions for polar coordinate. So what does that mean? It means that the solution should be periodic in theta. So if you go around the circle once and then you go back again, you want this solution to have some sort of periodicity because you are in polar coordinates. So to ensure that, and without going into further details, we consider solutions which have this form for B, and where B is I times n. I again is the imaginary unit, and n being an integer. So n integer. And if you look at A, basically that would, if you just substitute for B, so A becomes an integer. So if we just consider this and you use Euler's formula, and you remember last time when I was teaching you the solution using separation of variables in Cartesian coordinate system, if you take into account the multiplicity of the roots and do all the math, you get the solution which we call Mitchell solution. So I don't go through those derivations, but Mitchell solution, the form is extremely important, and we are going to get back to that very often. So let's just acknowledge that we have to go through a lot of steps, and then I just write the solution. If everyone will be happy with that, right? So using Euler's formula and accounting for the multiplicity of the roots, everyone knows what I mean by that, right? Last time we talked about it. And I add considerable patience, right? Okay, so a lot of dots here because that will take a while to do. This is good for rainy days, which are very often now in a state college. If it's rainy, all your friends are out of town, you have nothing better to do, just sit down and just go through it, and afterwards you feel better. Yeah. Then you get basically what we set out to get, the so-called Mitchell solution. And again, we are going to look back at this solution many times. So I'm going to write it because the terms are interesting to look at, although there are many terms. So everyone ready to write the solution? So we have the first line that you are going to see will actually solve a lot of different problems is a0 plus a1, that's the natural logarithm of r. John, did you say something? Oh. a2 r squared plus a3 r squared log r plus, where does this log r coming from? Exactly. So what you get from the formulation will be in terms of C, right? And then you have to change the C back to R. So then we have A4 plus A5 log R plus A6 R squared plus A7 R squared log R times theta plus, and then I'm using the same coefficients as in the book, so to make things easier, A11R, A12R log R, A13 over R, A14 R cubed, A15 R theta, A16 R theta log R, everything multiplied by cosine theta. And a very similar expression, so I use B at the end multiplied by sine theta. So B11R plus B12R log R plus B13 over R plus B14 R cubed plus B15 R theta plus B16 R theta log R sine theta. Not done. Well, you should be happy when you see a lot of terms in a general solution. Why? Why should we be happy about it? Gerald? Was it Gerald? Because you can, you see, all of the terms, this is all the solution to your equation. So if you have something which has a lot of different terms and a lot of a structure, that means that you can pick and choose the part of the solution which will fit your problem and develop a solution. And this is exactly what we are going to do next. So you will see if the problem is axisymmetric, we go back and look at this solution very carefully in front of us. We look to see, okay, for an axisymmetric solution, which part of it would actually make sense? We don't just plug it in blindly. And then you take those parts, you work with that. If it was very small, then it would be very limited in implications. So be happy that it has so many terms. I'll look at a few things just even now before we go to the example. So just be patient. One more line. So this one has a summation. So actually a lot of things are there, right? A n1 Rn plus a n2 Rn plus 2 plus a n3 or negative n plus a n4 or negative n plus 2, and this will be multiplied by cosine now n theta. And finally the last part, and as you may have guessed, has a similar form for sine. So let's add that these are constants, right? Where A, I, let's call it A, Ij, B, Ij are constants to be determined. So, observations. So now we wrote it down. We want to look at it, basically. It's hard even to fit it all in one screen. Okay. What do we see in this solution? In the beginning, I told you that some of the applications that we want to use this for involves a stress concentration. When the value of a stress, the value of the field that you are studying may become very, very large. Does this solution have that potential? Can you make the value of this solution very, very large? What do you have to do? But how? Yeah, but how would you do that? If R becomes very small or very large, this solution can become very, very, very large, right? Because you have terms where it is 1 over R, and then you have R squared, right? So that's a good thing, because you will see that sometimes we need to have this condition. So basically the way I would write it here is that the solution has the potential to be unbounded. You can have some unbounded solution here from this. And that's a useful thing if you are studying a stress concentration, and if the hole is very tiny, or if you are looking at very sharp corners, you want to have a solution where the values can become very, very large. Another very interesting property is, look at some of the terms here, they have theta in them. Like here, here, here. So theta is inside the term. So what does that tell you? It tells you that you have a situation where you have the possibility to have a solution where if you start from here and it's okay that it depends on theta, but if you go around and go back here, at the same point, you are going to get a different value potentially. Does it make sense? So if it depends on theta, it means that if you take this point, you go once theta is, let's say, 30 degrees. You go around 360 plus 30, it's a different theta, and then you have the possibility to have a different value here. Is this a good thing? Yeah, most of the time you don't like it, right? And you can get rid of this. How you would get rid of? You would just zero the coefficients of those terms which depend on theta, if you don't like it. But it turns out that there is one very important application where you actually need that. Can you think about that? We are all in 2D. 2D. Don't make, don't think about something overcomplicated. No. Okay, I'll tell you because I can't wait to tell you that. So if you consider a crack, okay? So the crack in reality, if you have a microscope, you go and see it's an opening, right? But how many of you, I know that some of you, your work somewhat is related to a crack. You have seen a crack, right? How many of you have any affinity for cracks? A little bit, yeah. So if you go and look in the microscope, there is an opening. But normally, mathematically, in a lot of contexts, you don't model the crack with its opening. How do you model the crack in elasticity? You just model it as like an interface, where you have two faces which are like this. Now, why this has any relationship to what I just told you before, to the multi-valuedness of the solution? Okay, now look at this crack here. I put my polar coordinate system here. This is my reference, and this is a tiny crack. So this crack, this point, this first point is theta equal to 0. I go back around the circle, I come back, and the point on the top, it's theta equal to 2 pi, right? I can devise a solution where the value is different below the crack and above the crack. This is very useful because the crack introduces a discontinuity in the displacement. So if you have a possibility that your solution can allow you to have this multi-valuedness basically at one point, then you can use it to solve a crack problem. So.
You still physically bounded to pi. There's not a physical angle that forces.
We'll solve this problem, right? We'll solve this problem. You will see exactly how it goes. I remember your question, and in exactly 2 classes, then you are going to see exactly how this works. But my point being that multi-valuedness is not necessarily a bad thing, which you see. At the same time, most of you said this is a bad thing. So if it is a bad thing, if this is not something physical in your problem, you just silence those coefficients which would cause multi-valuedness in your solution. This is how you would work with this Mitchell solution. Okay, so let's start with axisymmetric case. We still have 10 minutes, so we can get started with the first set of solutions for axisymmetric problem. So let's give it a title. What happened? Okay, I don't know what happened, so I just closed it. Let's see, it's better. Axisymmetric solution. So what does axisymmetry mean mathematically? What happened? What does it mean mathematically? If the problem is axisymmetric, but what does it mean now looking at the solution? So it means that there shouldn't be any dependence on theta, right? It doesn't matter what direction you look at, you are going to see the same solution. Now, if you look very carefully at the Mitchell solution, and this is what we are going to do in the next few classes for every example. So what terms do you think I have to keep to develop an axisymmetric solution? The first line, does it look good? How about the second line? That's for sure a no-no, right? There is a theta at the end, and then you have cosine theta, you have sine theta, cosine. So you see, this is why it is good to have a large solution. So simply, for axisymmetric solution, you just say, well, all those other coefficients have to be 0 because that just doesn't work. I only can keep that first line, and that's what we are going to do. So we focus on, I think I have to print out the Mitchell solution, so you have a printout always, so you can always go back and look at the whole solution to pick up the good part. So we only consider basically a solution which has this form. I forgot to ask you if you can think about any physical problem, anything that is actually axisymmetric, just a simple thing. Pipes, tubes, yeah, so this is obvious. Another question, if or a comment, when a problem is axisymmetric, the loading has to be axisymmetric too. I see this as a common problem with the students. It's not only the geometry. So if there is a pipe, but the loading is directional in some sense, you cannot use axisymmetric solution for that. So everything has to be axisymmetric. Boundary conditions, which loading included, and the geometry, everything. And then we have to basically, like before, now you have to write the stress, now that we have the phi, and that would be a good exercise for everyone to do, because I gave you the relationship between a stress and phi, and just to stay up for another 4-5 minutes, let's do this together. Remember that the relationships are a little bit more involved. So now just substituting phi, Do you think you still have energy to do some derivation? It's too late. Okay. So you see that in this case for stresses we have three constants A1, A2, A3, which we need to use boundary conditions to obtain them. We will see. Yeah, so like before, then we have to develop a strain solution, etc. So I guess I just stop here because I see that, yeah. So, okay, so I'll see you on Thursday and then we'll start with the examples. Derivations are done.